So what we want to talk about in this video is friction, or in practical terms, this controls the clumping of our grain. And before we move on, let's really quickly go through the setup. We have our grain source here with a certain point separation, and this will be reflected in the p-scale so that the pop grains know what to do. And of course, very important, I set the min and max substeps to something pretty high. In this case, 20, not massive, but a good middle ground for speed and accuracy. And then of course, a pop object that brings in those points from outside. And I added a little bit of a pop sprite and pop color to make our grains look a bit nicer. And of course, some lighting, which is not reflected in the pop grains. That's just how they work, because the pop sprites are used here and are not using the light. But yeah, pretty basic setup, nothing special about it. So far we have only used grain that is basically very dry. So it's almost like little balls that collide with each other, but they are not very sticky or anything. They really just fly away. And we can see that here, those are the default behaviors. You can see the grain spheres are rolling away pretty far. So there is some clumping happening in the middle. Here you can see they kind of build a small little hill. So there is actually some friction happening, but it's by default set to really low so that you get the behavior of relatively dry sand. So let's control this further. And before we look into this, one thing to repeat, which is very important, you might, out of a habit, might be tempted to go into the pop object and maybe lower the bounce forward to 0 and the friction to something really high. And let's do the same for the ground plane. High friction, no bounce forward and no bounce. And you might already guess what I'm talking about. This will not work because, as we talked about, the pop solver kind of loses control as soon as you put in a pop grains node, and this takes over, and this will also now take over the whole calculation of, something similar to friction. Because technically, remember, we are working with PBD, so the objects are actually not really calculating friction or anything. They are really just correcting their position in space. So these kind of physical properties will not work anymore. But the good news is, in the pop grains, we have actually our own friction. Now, the weird thing though is it's already set to 1, and it differentiates between colliders and particles, so itself and everything else. And you might think, well, maybe I can increase it to something higher, but that doesn't work. It's already set to the maximum. So unfortunately, that's not how it works. It's a bit more complicated, and what we need to understand are those two numbers here, static threshold and scale kinetic. Now, if you make the unfortunate mistake of trying to read the help, then you will get very confused, because it says here for the static threshold, the speed versus collision depth ratio at which particles will try to come fully to rest within a constrained iteration. What the hell does that mean? I tried to translate this to simpler terms. Basically, what those two numbers mean is, the idea is here a little bit similar to the dynamic friction that we talked about very early in POPs. And that is, the slower a piece is, the slower a piece of grain is, the more sticky it behaves. That's kind of the idea, or the more friction it has. So if you have a grain particle that is super fast and gets in contact with another grain particle, when it's very fast, it will create no friction whatsoever. But as soon as it falls below a certain speed, and that speed is defined here with a static threshold, 0.5, then it will be considered sticky or with friction, and then it will lose its kinetic energy, so its speed, by this amount with every iteration. So what that means is, the first number defines what points are considered, let's call it sticky, even though sticky is the wrong word here, but what points are considered with friction. And that means the higher the number is, the more points will be stopped, let's call it this way. And the second number defines how much they will be stopped. So if you have a higher static threshold, let's start with that, and we run the simulation again, more points will have some kind of friction. But what you can see is, yeah, sure, definitely something has changed, because when you remember how it was before, we didn't have such a high hill. The hill became actually higher, but when we look at the further pieces, not that much has changed, and this is why this by itself is not enough. But nonetheless, let's play around with this first a bit more, and let's set this to 2 maybe. So that means even points that have a speed of 2 will still be considered as stoppable, let's call it, and will stick to other points. And we will see this again, not so much on the points that are very fast and go very wide or very far away, but on the points that are actually creating a hill here. So now we have a hill of, I don't know, maybe 5 layers or something like that. So the hill got higher. So this is definitely important, but what's even more important is the scale kinetic, because this will define how strongly those points will stop. So let's increase that to maybe 0.5. And now we should see a real difference, because not only will more points be stoppable, but what's more important is how much they will stop, which is much more now. And we can see we have way fewer points that run away, and also our hill became higher overall. Now, if you're not careful, now it's great that we already got that. If you're too aggressive with this though, then this can happen, that you have grains that kind of fall down, hit another grain piece or particle, and then instantly stop, and you get those weird super thin lines. So it is, a balancing game to get this right. So let's quickly play around with a really high number. I don't know, maybe 4 and 0.8 or something, which is really aggressive. And you will see that the behavior then is kind of unrealistic. See, there you have it. Not only does it, stop too quickly, which looks weird, it also creates those annoying little towers. I mean, this goes away the higher your resolution is, or you will see less of it. But this is how it looks when you were too aggressive. You get those little, grain towers, and instantly stops in a pretty unrealistic fashion. A number that I usually start with, it's just something that I noticed that works well for me, is 0.7 and 0.3. So this is what I usually set as a default to get, in my opinion, relatively realistic starting point, and then I go from there. I would be really careful with going higher than 1 for the static threshold and going higher than 0.5 with the scale kinetic. I would be a bit more careful and make smaller steps when playing around with this. But here you can see with this number, I have something that sticks together way more already and feels way more like wet sand. One small note on top of this, when you change the substeps, so what I have here on the left is a pop solver with substeps of 20, and on the right a pop solver with 40, then you will at first not see a difference. But when you look closely, you can see there is actually a difference. So the stopping happens quicker, so to say. So it can actually change your behavior when you change your substeps. Just keep that in mind, and you might have to adjust the numbers a little bit. We will talk in the next video about other alternatives to this. This is, like I said, kind of the simplest form of clumping, which is already pretty good for most cases. But if you need something that is really strongly clumping together like snow, then this will not be enough. And then you need more. You need a built-in function that is actually called clumping that really clumps pieces together, which is much slower, but can create stuff like snow and so on. But for sand clumping, let's call it, or simple clumping, the friction should be your first tool to attack this, because it's really fast to use and can give, for sand at least, pretty convincing results. So I hope that made sense, and it gives you additional control over your grain simulations. So thanks very much, and see you later. Cheers.